Hi, I'm Dean. I'm going to be presenting on a joint work with Keren and François on distributed listing of cliques. Let's start with the overview. Okay, so we talk about subgraph existence problems. We're given an input graph and a small subgraph, and we want to know in which regions of the input graph the subgraph exists. This is a very fundamental problem both in distributed and in sequential works, and has lots of applications. For instance, lots of algorithms want to know in which areas of the input graph triangles exist because that allows them to run faster. Subgraph existence problems are divided into lots of categories. We consider three main categories: detection, counting, and listing. Detection just wants to know if the subgraph exists anywhere in the input graph. In a distributed sense, we'd want that at least one node in the graph will just say that it sees some instance of the subgraph. In the counting sense, every node will output a value, and the sum of the values will be the total number of instances of the subgraph in the input graph. And the hardest case of all is listing. In listing, we want to actually get a list of all the instances of the subgraph. For example, in this input graph, we have these three triangles. And we want every node in the graph to output a list of some triangles such that the union of all the lists is exactly these three triangles. In distributed computing, there are lots of different models. If we look at synchronous models, we have three major models: local, congested, and congested clique. They differ in two different factors. In the local model, messages between nodes have unlimited bandwidth, while in the congested and congested clique, every message is at most log n bits. On the other hand, in the congest and local models, nodes can only communicate with their neighbors in the input graph. Basically, the input graph is the same as the communication graph. While in the congested clique, every node can communicate with every other node. That means we have one input graph, and the overlay network for the communication is a clique. Consider the following trivial algorithm for solving KP listing. KP listing is to list all instances of cliques with P nodes. Every node just sends all its neighbors to all its neighbors. In the local model, this will take one round. In the congest and congested clique models, this will take many rounds. Since it takes one round in a trivial manner to solve this problem in the local model, this problem is only interesting in the congest and congested clique models. And so that's where our results lie. We show the first algorithm in the congest model, which solves KP listing for all P in a sublinear number of rounds and non-trivially. This also improves upon the state-of-the-art for K4 and K5 listing, which were previously known to be sublinear. However, we're the first for K6 and above. In the congested clique model, we show an algorithm for KP greater than 4 listing, which is sparsity aware. That means it becomes faster if the input graph is sparse. These problems received lots of attention recently, from considering just subgraphs, which are cliques, and even cycles and trees. And so we have a very rich communication complexity landscape for these problems. We focus on the landscape for listing and detection and counting of cliques. In the congested clique model, almost a decade ago, an algorithm was shown to perform KP listing. Later, many years later, it turned out that this algorithm is tight when matching lower bounds were shown. For the case of K3, however, it was shown that it's possible to count K3 much faster using algebraic methods and matrix multiplication. However, problems in the congested clique which have small output pose difficulties in showing lower bounds for them, as lower bounds for these problems would imply lower bounds for circuit complexity. And so no lower bounds are known for K3 counting in the congested clique. For this reason and others, an entire new branch of work developed for sparse listing. It was shown that for K3, it's possible to tightly list all instances of K3 in the input graph, and do this faster if the input graph is sparse. We show, for K4 and above, an algorithm which turns out to be tight with respect to the sparsity as well. And so now, one would want to take these results from congest and move them to the from the congested clique and move them to the congest. However, we're met with inherent difficulties from the models. These algorithms in the congested clique that we talked about before work with sending lots and lots of messages and to distant areas of the graph, two things that can't be done in the congest. And so in the congest, what happens is that even if we have dense regions, they can't help out any other region. So this means that every single region will have to fend for itself and perform KP listing for itself, and sparse regions will have to use more novel techniques than in the congested clique in order to be able to send less messages because they have less bandwidth. And so, many researchers set out in order to show this for K3 in the congest. And after a really long line of works, which involved lots of different techniques, it was shown how to perform K3 listing in the congest in a tight manner. However, no better results are known for detecting K3. Further, the only lower bound we know for detection of K3 is that we require more than one round, and that's because all the techniques we know for showing lower bounds break for K3 and congest. So what happens when we go beyond? What about K4, K5, K6? Well, it turns out that the lower bound for listing is actually rather trivial to extend. However, no upper bounds were known for many years. Recently, a paper showed two upper bounds for K4 and K5, which were sublinear.
This beautiful work was very pioneering and opened the door for listing algorithms not just for K3, but also for general KP and the congest and sublinear number of rounds.
In our work, we show one algorithm which tackles all of KP at once and shows sublinear and rather efficient algorithms. Recently, we also collaborated with Ija, and we have new results which are yet unpublished and show a tight algorithm for listing all of KP in congest. When it comes to detection, it's easier to show lower bounds as the problems are harder compared to K3, and so polynomial lower bounds were shown for detecting KP greater than 4 in congest. Okay, so how does this work? How does K3 work? How can we get it to work for K4 and K5 and above? Well, K3 works with expanded decompositions. Expanded decompositions take a graph and break it up into clusters where every cluster is very, very tightly packed together, and nodes inside clusters can send messages to each other very easily, and there are a few edges between the clusters. This is accompanied by routing results. Routing results inside the clusters basically state that the clusters can function as small congested cliques, in the sense that every node can send a message to nodes far away from it in the cluster, and the message will be delivered very, very quickly inside the clusters. Okay, so how do we use this for K3 listing? Well, in previous works, what was done is as follows. Every cluster looks at the edges which it itself knows, and just lists all the K3 that it itself sees by executing some sparsity-aware congested clique algorithm. Now notice that once every cluster lists all the K3 that it sees, every edge which is completely inside the cluster has already had all the K3 which it itself is a part of listed. And so we can remove all the edges inside clusters. And we can remain with a graph which is much, much smaller. Since we show that the number of edges inside the clusters was at least a constant fraction of the total number of edges, within log n iterations of this technique, all the K3 in the graph can be listed. Well, what happens with K4? With K4, we get a new challenge. Let's try to do the same thing as K3 and see what happens. Well, take a cluster sees its edges, and tries to list all the K4 which it itself sees. But take a look at this K4. This K4 contains this edge which is completely outside the cluster, and no node in the cluster knows about this edge. And so the cluster has no ability to list this instance of K4. This is a step more difficult than the case of K3, because we can't just tell every cluster to list what it sees and get rid of the edges inside the cluster, because we'll miss some K4. In a previous work, they tried to tackle this problem. The way this problem was tackled, some edges were brought into the clusters, while some edges were sent out of the clusters, and so the task of the listing was distributed to the cluster itself and the nodes outside of it. Let's see this for example. So for instance, take this K4. Either this edge could be sent into the cluster, and then the cluster could see the K4 and list it, or this edge could be sent out to both of these nodes, and these nodes, since they're neighbors outside the cluster, they could communicate and figure out that they're together in this K4. And so the listing, the K4 listing problem is now split between the clusters and the nodes surrounding them. However, when we go to K5 and above, we get another step of complexity. Let's say that we try to do the same approach, and that we try to take this K5 and take this edge and move it outside to these three nodes, and have these three nodes decide to get to an agreement together that they're in this K5. Well, inherently, that would mean that these three nodes will have to know that they're in a triangle together. And so this problem is more difficult than performing triangle listing outside the clusters. But because the nodes outside the clusters aren't in a cluster necessarily, then they can't necessarily communicate very efficiently together with each other. And so asking them to perform triangle listing is a problem which is very, very difficult. In the previous work, the way this was tackled was by changing the parameters of the expanded decomposition and just trying a brute force solution and this got a sublinear result, we want two things. The first thing is we want a single algorithm which will work for all of KP. We don't want to distinguish between KP 4, 5, 6, and so forth. We want to tackle it all at once. And the second thing is we want to go much faster. To do that, we have one major takeaway from the previous challenges, and that is that we have to perform all the listing inside the clusters. This is because when we go above p equals 5, it becomes very difficult to do any listing outside the clusters. This leads to two challenges. The first challenge, every cluster must be able to learn some of its surrounding. We have to bring in edges into the cluster. Notice that this does not mean that we have to bring in all the edges incident to nodes which are incident to the cluster. We just have to bring in all the edges which could potentially form a KP with some node in the cluster. Also, we should do this in a load balanced way, because if we bring in too many edges to one node in the cluster, it could be problematic. The second challenge we have is problem size versus bandwidth. Say, for example, that we take a congested clique with k nodes. It was shown that if we give an input graph with k-squared edges, it takes k to the 1/3 rounds in order to be able to list all k3 in this congested clique with k nodes. Also, it was shown that if we give less input and more sparse input, it takes less rounds. The contrary should be true as well. If we give these k nodes somehow an input graph with more than k-squared edges, it would take more than k to the power of 1/3 rounds in order to solve triangle listing on this input graph. This intuition carries over to the congest. If we have small clusters, and with not lots of edges inside those clusters, and we bring in lots of information into these small clusters, the small clusters will be overwhelmed and just take way too many rounds in order to perform the listing. As such, we get these two challenges. The first challenge, we overcome an n to the power of 3/4 rounds, regardless of the value of p. The second, we overcome an n to the power of p divided by p plus 2 rounds, which is very, very close to the lower bound of n to the power of p minus 2 divided by p. For convenience, we color code the challenges. The first challenge is blue, the second is purple, and whenever we have a step in our algorithm which solves one of them, it has the corresponding color. If we have a step which solves both challenges at once, then it has a mixture of the two colors. Our overall approach, which we use for both challenges, is controlling the sparsity of the algorithm in many different places very, very carefully. In layman terms, the way we do that is we deal with what's simple now and delay the hard stuff to later. If you see an edge or a cluster that is very easy to deal with, very easy to list the KP with that edge or that cluster, do it. The difficult ones, leave them for later. And the reason this works is when we deal with the easy ones, we slowly remove clusters and edges from the graph, and so the graph itself becomes sparse. And so what is difficult now will be easier later. Okay. So how do we deal with the first challenge? The first challenge we deal with by identifying nodes inside the clusters, which are problematic. Problematic in the sense that if we want to list KP involving them, we'll have to bring in lots of edges into the cluster. We identify these nodes and defer treating their incident edges until later, when the graph is more sparse and when it's easier. For the second problem, we have to deal with it in two different ways. The first, we control the surroundings. We make sure that whenever we deal with a cluster, it's dense with respect to its surroundings. This means it doesn't have to be dense in an absolute manner. It doesn't have to have lots of edges, but it has to be dense with respect to its surroundings, because otherwise it won't be able to cope with information that enters it. We do this by decreasing the arboricity in an iterative manner in the entire graph. We make sure that the arboricity of the graph is always roughly equal to the minimal degree inside the clusters that we consider. We want to be able to perform a sparsity-aware algorithm inside the clusters in order to use the fact that we're running on a sparse input graph, and so we can run faster. Also, we have lots of load balancing to perform within the clusters themselves to make sure that no node sends or receives too many messages. Okay, so how do we implement this? Well, we use the first expanded decomposition of the two, which are known in CONGEST. This expanded decomposition gets an input graph and a value delta after n to the power of 1 minus delta rounds. We get, it splits the edge set E into 3 sets, EM, ER, ES. EM is a set of clusters. Every single connected component in EM is a cluster. This means that it has a minimal degree of n delta, and at the same time has very low mixing time, which mixing time allows us to use the routing techniques inside the clusters and basically say that every single node in the cluster can send and receive messages from any node inside the cluster, and can send and receive roughly n to the power of delta messages per round inside the cluster. Further, we have the notion of ES. ES is just a set of edges with low arboricity, has arboricity at most n to the delta, where arboricity means that is the minimum number of trees that we can split ES into. And finally, we know that ER is the remainder edges, and it's at most a sixth of the total edges that we had at the beginning. Now, the expanded decomposition is very non-standard. Usually, expanded decompositions do not have ES and do not have the minimal degree. That's the way it usually is also in general computer science. However, this expanded decomposition, and that's also the way the second expanded decomposition in CONGEST works, the newer one. However, in our case, this is really required. We need this minimal degree inside the clusters in order to be able to deal with all the information that's coming from outside. Because if we don't know minimal degree on the clusters themselves, if we can't say that they'll be able to deal with the information which enters them. And so, while the first expanded decomposition in the CONGEST, this expanded decomposition, did not intend to have this arboricity factor and the minimal degree factor, we benefit from this in a surprising way. The general idea that we follow is to make sure the minimal degree in the clusters is roughly equal to the graph arboricity. Well, how can we achieve that? What if we ran the expanded decomposition with delta which is roughly equal to 1? Well, then it will run really fast, and we'll get really, really dense clusters. Our clusters will almost be linear in size, and they'll have lots of edges inside of them. Also, ES will have arboricity which is just a bit less than linear. Okay, well, what if we were able to list all the KP involving EM? Then we could throw EM out, and we can just ignore these edges now. And this is not so far-fetched because these clusters are very, very dense, so even if we bring in edges from outside, they should probably be able to deal with it. Let's also assume that somehow we get rid of ER. Then we're left with ES, and we can recurse on ES. And since ES has arboricity slightly less than linear, we can use delta 2, which is slightly less than delta 1. And we can keep on recursing like this, and make sure that at every time, the minimal degree in the clusters is roughly equal to the graph arboricity that we consider. Let's formalize this. Say we have an algorithm list, which gets a graph with arboricity A. If the arboricity is small enough, it just tells every node to broadcast all the edges which leave it according to the arboricity. And this is done really very, very efficiently since the arboricity is small. Otherwise, it splits the graph into two sets of edges. EM hat, where all the KP involving edges in EM hat have already been listed, and so we can remove EM hat from the graph. And ES hat, which has arboricity at most half of what it was before. And so if we recurse this for log n times, we're able to list all the KP in the graph. So how do we get the algorithm list? Well, what does it do? It wants to take an input graph and give you a graph with half the arboricity. So let's run the decomposition with n delta equals a divided by 2. Then yes, we'll get ES with half the arboricity. But even if we manage to take care of EM and list all the KP involving EM and throw EM out, we're still stuck with ER. So what do we do with ER? Okay, well, let's try again. Let's run the decomposition with a slightly lower delta. Now we'll get that ES has arboricity at most a divided by 2 log n. Assume that we get rid of EM by doing all the listing. And now we're left with ER, which is at most a sixth of the edges before that. So we can now recurse on ER. And every time we get these new ESs, we can unite them together. Since ER always decreases by a constant factor, this will take a logarithmic number of steps. And so in the end, all the ESs that we get together will have arboricity at most a divided by 2. Okay, let's also formalize this. So assume that we have an algorithm ARB-LIST, which gets an edge set which is broken into ES and ER, such that the arboricity of the entire algorithm and the entire graph is at most a. And it splits the entire graph into 3 edge sets: EM hat, ES hat, and ER hat. EM hat has the guarantee that all the KP involving EM hat have already been listed, and so we can throw EM hat away. ES hat has arboricity just a bit more than ES, and ER hat is a constant fraction of the number of edges in the original ER. Okay, so how do we get this algorithm? So assume that we have this algorithm. How do we prove algorithm list? Well, algorithm list gets a set of edges in E, set ES to be the empty set, ER to be E, and run this algorithm. Then reset ES to be ES hat and ER to be ER hat. And observe that within log n iterations of this algorithm, ER hat will be empty and ES will have arboricity at most half of what it was before. Okay, how do we show this? Well, the overview is as follows. We take ER, we decompose it. After we decompose it, we take the ES prime part and add it to ES. Then we take a subset of EM prime, and we call that EM hat. And the rest we move to ER hat. And we do this in order to be able to list all the KP involving EM hat. Okay, so now the question becomes is, how do we select EM hat such that we don't have to move too many edges from EM prime to ER hat? And that we also can list all the KP involving EM hat. So say we ran the decomposition and we get a cluster. Observe nodes outside the cluster. If a node has lots of edges going into C, it's called C heavy. Otherwise, C light, and the cutoff is n to the 1/4. If you have more than n to the 1/4 neighbors in C, you're C heavy. Okay. Now look at the nodes inside the cluster itself. If a node has lots of C light neighbors, we call it a bad node. Otherwise, it's a good node. Intuitively, there shouldn't be too many bad nodes because inherently there aren't too many edges between C light nodes and the cluster C itself, and so there can't be too many nodes inside of C which have too many light neighbors. What we'll want to do now is we'll throw away into ER hat the edges which are between two bad nodes and keep all the rest of the edges in EM hat. Since we don't have too many bad nodes, this won't send too many edges away. Okay, now that we've done this, we want to bring in all the edges to the cluster, which could potentially form a KP with the edges of EM hat. Okay, so C heavy nodes just observe their neighborhood and send all the edges directed away from them to the nodes inside the cluster which they have. And this is done very quickly because they have lots of nodes inside the cluster. For C light nodes won't be able to send in all the neighborhoods which surround them because it's too large. But practically, these neighborhoods don't really interest the cluster because lots of those edges can't form a KP with the cluster itself. And so in order to bring in edges from C light nodes, every good node inside the cluster will observe its C light neighbors. But recall that it doesn't have too many because it's a good node. It'll send all of its C light neighbors to all its C light neighbors, basically letting them know about each other. And so if an edge exists between two of its C light neighbors, they'll be able to send that edge into the cluster because they'll know that perhaps this edge will be useful for some KP with the cluster. This won't take too many rounds since good nodes have a low number of light nodes outside the cluster. Okay, so we brought in all the edges which could potentially form a KP with edges in EM hat into the clusters. What do we do now? Well, it turns out we have to load balance. So we brought in edges from outside the cluster into the cluster, and we want to make sure that every node in the cluster has roughly the same number of edges it's responsible for. We're off to a pretty good starting point since the way we brought in the edges ensured that every node inside the cluster doesn't already know too many edges from outside. However, this isn't good enough, and so we need some further reshuffling techniques. We won't be able to get into these techniques too much now due to lack of time. But since not too many edges entered every single node in the cluster, and the minimal degree in the cluster is very high, it turns out that we can perform the shuffling very, very quickly. Likewise, now we want to be able to perform the listing itself with all the edges we brought in after we did the load balancing. And so we design a randomized algorithm which is sparsity aware and does this. The way it works is every cluster takes the nodes it's aware of, that means itself and all its incident nodes, and creates a randomized partition for them. Every node in the cluster chooses some parts from the partition and learns all the edges between those parts. This allows the cluster to be able to list all the KP which it can know. Also, we do this in such a way that every node receives at most A times n to the power of p divided by p over 2 messages during the listing. Since the minimal degree in the cluster is roughly also A, then this takes n to the power of p divided by p over 2 rounds using the routing techniques inside the clusters. Notice that this is exactly the point where we need the fact that the arboricity of the graph is close to the minimal degree inside the clusters because they cancel out and give us the runtime that we desire. Finally, it's possible to take the algorithm we design here and see that it's an algorithm on its own in the congested clique, which turns out to be tight with respect to the sparsity. To summarize what we did, we have two major results. The first sublinear algorithm for listing in the congest, for listing KP, and a tight sparsity-aware algorithm for listing KP in the congested clique. With regards to algorithm contributions, our paper is the first paper which uses decomposition technique with a series of decreasing deltas and with these two iterative approaches. These approaches could be useful for independent work in order to be able to use this standard decomposition in better ways. Further, we showed how in a load balancing way we can bring in lots of information to the clusters and how we can perform sparsity-aware operations in the clusters themselves. That's it for today. Thank you.